Prior to our break, we developed a flowchart of a program that would allow us to place numbers in sequential order. This program may be functionally divided into 5 major portions: comparing the numbers, switching them if needed, checking the limit to see if we've handled all of the numbers, then checking for done to determine if all numbers are now in order, and finally, if we're not done, resetting the pointers and stepping through the program once again. Now we're going to discuss each one of these functional areas separately. But before we do that, let's talk about the initial conditions that will first have to be set up. There are 3 initial conditions that must be taken care of before we can start the program. We must set up a left pointer, we must set up a right pointer, and we must set up a limit. We set up these 3 initial conditions by using the immediate addressing mode, which is mode 2 used with register R7, the program counter. In our example, we wanted to set the limit at memory location 604, so we use a move number sign 604R0. This instruction moves the number 604 into register 0. We use similar instructions for the left and right pointers. Thus, we move the memory addresses into registers R1 and R2. Notice that the right pointer is always 1 byte address higher than the left pointer because we're dealing with bytes of data. Now, let's discuss the first functional block in the flow diagram, comparing numbers. The first 2 blocks in the flow diagram tell us we must compare 2 numbers and then increment the pointers. We can perform both of these steps by using the compare byte R1 plus R2 plus instruction. This instruction compares the contents of the location specified by the left and right pointers, then increments both pointers. Next, the decision block asks if the numbers are in order and is implemented by the BMI check instruction. If the answer is yes, we want to branch to the next functional block, which is check the limit. However, if the result of the comparison is not minus, then we know that the numbers must be switched around before going further. As you can see, if the comparison result is not minus, the branch does not occur and the program goes directly to the next functional block, which is labeled switch. Since we're talking about switch, let's now discuss the functional block of the program that performs the switching of the 2 numbers. Here's an example of what we're trying to do. You can see that prior to the switching operation, the 2 numbers are not in ascending order. Notice that after the program executes the switch, they are in the proper order. Let's see how the program accomplishes this switching function. If we make our first number a source operand and the second number the destination operand, our first step will be to save the destination operand so we don't lose the number. Therefore, we move that number into a general purpose register for temporary storage. The next step would be to move the source into the destination location. In other words, move the number 6 to the next location. Our third and final step would be to move the former destination, which we've been holding in a GPR, back into the source location. Once we've done this, we've effectively switched the 2 numbers so that they are now in the proper order. Swapping 2 numbers around is not as easy as it sounds. In fact, when choosing instructions to do this job, you might find that the 2 pointers in particular can trip you up. Because this step might be a little tricky, we're going to go through it carefully. Here are the conditions that exist after the compare. We've compared the first and second numbers, our source and destination operands, but the 2 pointers are now pointing to the second and third numbers. You can see our problem. We want to switch the first and second numbers, but we have no way of getting to them both because the pointers are pointing to the second and third numbers. Well, at least one pointer, R1, points to the second number. So let's start there and take the rest a step at a time. We have said that the first step is to save the destination. Because the left pointer, R1, is pointing to the destination, we can use a move byte R1, R3 instruction. This takes the contents of the location specified by the left pointer, R1, and moves it into general register R3 so that it can be saved. Now, we're planning to move the first number into the location formerly holding the second number. Before we can attempt this, we must get both pointers back 1 location. Rather than use 2 separate decrement instructions to shift the pointers, Let's use the auto-decrement addressing mode, which decrements pointers R1 and R2 before performing the job specified by the move instruction. That's all we're showing here, how the auto-decrement mode can be used to move both pointers back one location. Once the auto-decrement has moved the pointers, then the move byte instruction can go ahead and perform its specified job. In this case, move the contents specified by R1 into the location specified by R2. You can see what this does. It moves the first number, or source, into the destination location. The final step is to move the former destination into the source location. In other words, move the second number, that is currently stored in R3, into the position formerly occupied by the first number. We can do this by using the move byte R3R1 instruction. This instruction moves the contents of R3 into the location specified by R1, the left pointer. Now, all we have left to do is get our pointers back where they were in the first place. To restore or increment the left pointer, we can simply use our instruction in the auto-increment mode. So once the number has been moved from R3 to the location specified by R1, R1 is automatically incremented, moving it to the next location. Now all we have to do is increment the right pointer, which we do with a simple increment R2 instruction. Thus, both pointers are right back where they should be. Remember, we want to indicate any switch that was made. We're going to do this by moving the octal number 1 into register R4. This action effectively sets the least significant bit in R4 and clears all remaining bits. Thus, the least significant bit serves as a flag. It is raised whenever a switch is made. Let's review the method used for switching numbers. We start out by using a move byte instruction to save the destination by storing it temporarily in general register R3. Then we use another move byte instruction with auto-decrement addressing modes to move back our pointers so we can move the source into the destination. Next, we use a third move byte instruction to move the former destination into the source. Part of the instruction uses the auto-increment mode to restore the left pointer. We then use a simple increment instruction to restore the right pointer. And finally, we use a move number 1 R4 instruction to indicate a switch was made. We've now compared our numbers and switched them if necessary. The next portion of the program we want to study is that of checking the limit to see if we've compared all the numbers required. Remember the last step in the compare portion of the flow diagram? It told us that if no switch were needed, we could go directly to the check limit portion of the flow chart. The last step in the flow diagram was implemented by the instruction BMI check, which says branch if minus to check. In other words, if the comparison shows the second number is larger, skip the switch portion of the program and go directly to the next program block, which is checking the limit. Earlier, we explained the method of determining the offset of any branch instruction. The question is, what value do we put after BMI in place of the word limit? We can see that the part of the program that checks the limit begins at address 1016. We know that the branch instruction itself is at location 1002. Therefore, what offset value do we use with this branch instruction? Did you remember how to calculate an offset? Were you correct? Did you calculate an offset value of +5? In the event you did not, let's review how we arrived at this answer. You are here at location 1002. The program counter is at the next location, and the offset is always calculated from the program counter. So to reach location 1016, we must move 5 words forward from the program counter, which is an offset of +5. Therefore, the proper instruction at location 1002 is BMI +5. Now, let's see how we check our limit. As you recall, we have a left and right pointer. The right pointer is always one location ahead of the left pointer. Let's use the right pointer in helping us determine when we reach the limit, because the right pointer will always reach the limit before the left pointer. In order to check the limit, what we would like to do is compare the address stored in the limit register R0 with the address in the right pointer R2. Thus, we simply compare R0 with R2 by means of a compare R0 R2 instruction. If the address in the limit register is not equal to the address in the right pointer, then we want to loop and go back to the start of the program. Because of this, we use a BNE, branch if not equal instruction, to go back to the start of the program. When checking the limit, if we find that the addresses of the limit register and the right pointers are equal, then we want to go to the next program step, which asks if we are done or not. Therefore, if the result of the comparison is equal, the BNE instruction cannot cause a branch, and we go to the next part of the program, which checks if we are done. This brings us to the next to the last functional block in our program, which asks the question, are we done? In checking for done, we use a BIT instruction to test the least significant bit in register R4. Remember how we used a move instruction to set this bit each time two numbers were switched? Well, if no numbers were switched, this bit would never have been set. Therefore, if we find it is clear at this point, it indicates we're done with the program. In other words, all of the numbers are in the proper order. On the other hand, if two numbers were switched, the bit test instruction will detect a 1 in register R4. This 1 indicates that we are not done with the program. Another BNE branch instruction can then be inserted after our bit test instruction. This BNE instruction causes a conditional branch back to the initialized portion of our program if the LSB is not equal to 0. The initialized portion of our program then resets the pointers to their starting addresses and clears register R4 so that we can recycle through the program. Note the first instruction in the initialized portion sets up our limit value. Since this limit does not change, we branch back to the second instruction. The CPU will remain in this program loop until the bit test instruction detects a 0 in the least significant bit position of R4. This 0 tells the CPU that no additional switches were made on the most recent pass through the program. In other words, all of the numbers are now arranged in their proper sequence. At this point, the not equal to 0 condition is no longer satisfied. Therefore, the central processor ignores the conditional branch instruction and proceeds directly to the next instruction, which halts our program. This is our entire program. Note that it's divided into 6 blocks. Initialize, in which we use 4 instructions to set up the limit register and pointers and reset register R4. The start of the program, which compares two numbers and then increments the pointers to the next two numbers. The switch portion, which uses 5 instructions to swap two numbers around if the second is not larger than the first. The check portion, which uses 2 instructions to see if we've reached the limit, indicating we've processed to the desired amount of numbers. The reset portion, which tests the contents of R4 and causes a branch back to the beginning of the program if we're not done. And finally, the done portion, which is simply a halt instruction to stop the program once we've finished. In our example, we've been talking primarily about 3 numbers. Suppose we wanted to sort a larger quantity. Say we might like to sort 25 numbers, or perhaps even 1,000 different numbers. How drastically would this change the program? Actually, it would change it very little. In fact, the only changes would be in the initialized portion of the program. In the first move instruction, we would simply put in the last address of our list of numbers, thereby defining the number of locations we want to deal with. This number would be moved into R0, the limit register. Then we could simply put the starting address of the list into R1, the left pointer, and the starting address +1 into R2, the right pointer. That's it. We're ready to go with no further program changes. This program is not just for numbers. It can also place letters into alphabetical order. Any letter used in a PDP-11 system is translated into ASCII code, which is then handled as an 8-bit byte. Here, for example, you see that the letters A through Z are represented by octal numbers 101 through 132. Thus, if we sort the numerical representation of these numbers and place them in order, we have, in effect, placed the letters in alphabetical order. We've spent so much time discussing the intricacies of the program that by now you may have forgotten the branch instructions themselves, unless we've just happened to use them in the program. Let's take a second to review what branch instructions you've learned. Remember these, the 8 branch instructions that we discussed earlier? 4 were used to test the 1 or set condition of the 4 condition code bits in the PSW, while the other 4 were used to test the 0 or clear condition of these 4 bits. Do you remember that at the very beginning of this section we mentioned that there were 16 conditional branches? You're probably thinking just about now, but you've only told me about 8 so far, 4 for the set and 4 for the clear states of the condition code bits. Of course you're right. So now let's talk about the remaining 8 branch instructions. Before we cover the remaining branch instructions, we'd like to talk for just a moment about signed versus unsigned numbers. -5 is an example of a signed number. In dealing with this number, we must consider not only the value 5, but also the sign indicating a negative or minus. An unsigned number is one in which we are only concerned with the value. We're not interested in whether it is a positive or negative number. Suppose we wanted to know if the value A was less than the value B. We could use a compare A-B instruction to find the answer. In this case, let's assume that these values in question are 6 and 7, and that they are both unsigned numbers. In other words, is 6 less than 7? In doing a compare with an unsigned number, the instruction subtracts the destination from the source. In this case, it subtracts 7 from 6. Notice that adding the 6 and -7 results in a negative answer. A negative answer indicates that the destination is larger than the source, or in this case, A is less than B. Notice that the computer is interested only in the sign at this time, and because it sees a minus, it sets the N bit. Therefore, we can summarize by saying if A is less than B, then the N bit is set, provided we're dealing with unsigned numbers only. Suppose we again want to know if the value A is less than the value B, but now we're dealing with signed numbers. In this example, we're going to compare a -6 with a +7. These two numbers are therefore signed. In this case, the compare instruction takes into consideration the sign of the source, the destination, and the result. Notice that a compare instruction subtracts the destination from the source, in this case 7 from -6. Because subtracting 7 from -6 results in both an erroneous answer and a change of sign, or an overflow condition, the CPU sets the V bit. Therefore, if A is less than B, then the V bit is set, provided both numbers are signed numbers. We can now put this all together and say that whenever the value A is less than B, either the N bit or the V bit will be set and will cause a branch. This is true for either signed or unsigned numbers. We have a single branch instruction, BLT, that handles these conditions. BLT, branch if less than. To summarize, the BLT instruction branches whenever A is less than B, regardless of whether signed or unsigned numbers are used. Notice that the BLT instruction tests more than one condition, unlike the other branch instructions we discussed before. The BLT instruction tests to see if the N bit is set or if the V bit is set. There are 7 more combinations of condition code bits that are tested by branch instructions. For example, one combination might test the N, Z, and V bits. Another combination might test the Z and C bits. You now know that the BLT instruction tests for a less than condition. We also have a BGT, or greater than instruction, which branches when A is greater than B. We can add another condition or equal to the BLT and BGT instructions. Now we have BLE, branch if less than or equal, and BGE, branch if greater or equal. We have 4 other branch instructions to check lower or higher conditions. BLO, branch if lower than, and BHI, branch if higher. BLOS, branch if lower or same, and BHIS, branch if higher or same. Notice that when dealing with the lower or higher conditions, the BLO instruction is the same opcode, in fact the same instruction as BCS. BLO is just another mnemonic that the assembler recognizes. The same is true for the BHIS and BCC instructions. This summarizes the 8 additional branch instructions. Remember that these instructions can be used with both signed and unsigned numbers. 2 instructions check for greater or lesser. 2 more check for greater or lesser or equal. 2 instructions check for higher or lower conditions. And the final 2 instructions check for higher or same or lower or same. This is a summary of all 16 conditional branch instructions. 8 branch instructions test only one condition, either the set or clear state of one of the 4 condition codes. 8 other branch instructions check multiple conditions, such as testing the N and V bits to look for a less than condition. Notice that the last 2 instructions in either case are one and the same. Technically, there are only 14 conditional branches if you are just dealing with the opcode. However, for ease of programming, we have assigned a different mnemonic to 2 instructions so that the programmer effectively has 16 conditional branches at his disposal. That completes our discussion of branch instructions. Before going any further, we'd like you to complete a series of exercises contained in your workbook. These exercises are very important and should reinforce your understanding of the PDP-11 instructions that we have covered up to this point. Please do not begin any new material until you've finished the exercises and checked your responses against the answer sheets provided in the workbook. When you hear the next tone, turn off this playback unit and proceed to the workbook exercises. After you've completed these exercises, you can continue with this study unit.